Thank you, Laura. Yeah, I know everyone's eager for the break, but I am here to talk to you briefly about planetary oxidation. So I want to start by asking which of these laser pointers is the right one to use. There's actually three of them. This one. Yeah. No. This one? No. This one. Yeah, there we go. Okay, I want to start a second time by acknowledging my co-authors. Firstly, Laura Schaefer, who you heard from in the great review talk yesterday. Rebecca Fisher, who is really a planetary core expert. And Feng Ding, my postdoc, who I will whose work I'll very briefly talk about at the end. So you have two examples here of oxidized planetary surfaces. The first is the surface of Mars as imaged from the Opportunity rover. And the second up here is not some sci-fi future scenario of Mars. It's actually Wadi Rum in Jordan, which is just one of the most incredible places that you could ever visit if you ever get the opportunity to go there. And in both cases, you're seeing here surfaces where the iron has been elevated to a high oxidation state, hence giving the classic reddish appearance. On Mars, this oxidation is driven by escape of hydrogen to space. On Earth, primarily, or at least by the biosphere, but it's really the abiotic oxidation part that I want to focus on here today. Okay, so before getting into the details of what we actually did with the modeling, with apologies to the chemists in the audience, and I think you're in the minority, so it's probably okay. I want to talk a bit about oxidation versus reduction in simple terms. So you may or may not remember high school chemistry. Oxidation is loss of electrons, reduction is gain. And a really nice, simple example of a redox reaction is iron reoxing with oxygen. Iron is less electronegative, so it hangs onto its outer electrons less well. Oxygen is more electronegative, so it oxidizes the iron from FeO to Fe3+. So reduced iron, like you see in meteorites, going to something like hematite in red beds on Earth. As I showed in the last slide, a great example of an oxidized surface in the solar system is Mars. A great example of a reduced surface, in this case, due to the presence of hydrogen in the atmosphere, is Titan, shown here. And it's really useful in a planetary context to think about if you have the whole periodic table, what kind of trends you get. This is showing here electronegativity, where red means more electronegative and gray means less. But the periodic table is complex, and we planetary scientists are very simple. So let's try and make things easier by just focusing on the elements which are most abundant. So you can already simplify things this way. It turns out magnesium and silicon both bond with oxygen fairly early, and then thereafter mainly remain in the mantle and mainly don't play much further role unless you're getting into really hot roaster type cases, which for terrestrial planets we're not going to consider further here. So let's eliminate those as well. And then we become left with this scenario where you have some oxidizing species over here. You have hydrogen, which we've learned extensively this week for terrestrial type planets, really wants to escape to space. You've got iron, which wants to sink to the core. And so in a very generic sense, you always should expect a situation where the surfaces and atmospheres of terrestrial planets should want to oxidize. And I think it's kind of neat to emphasize that this is purely an outcome of stellar nucleosynthesis. If we had, say, lithium as more abundant than oxygen, then it would drive in the other direction. So it's also good to look at some data. Let's do this in the solar system because we don't yet have this available for exoplanets. I'm an atmospheric scientist, so the first place I would start thinking about redox would be in the atmospheres of different planets. And of course, if you do that, you'll say, oxygen has this Earth has this really oxidizing atmosphere because of the presence of abundant O2. But as Laura hopefully convinced you all yesterday, this is not really the correct way to think about it, because actually it's the bulk oxidation state of the planet, which is much more important. And so a different picture emerges if you do that. I'm not going to belabor the mineral buffers because I know everyone remembers them from yesterday perfectly. And I've instead just put colors here to indicate that there's my interpretation, at least, of what the bulk upper mantle and oxidation state is of each of these planets. So Titan, we don't really know the interior composition, but it's so hydrogen rich that I think that highly reduced is a good guess. Moderately reduced for Mars, it's kind of interesting because Mars's surface is highly oxidized, but actually its upper mantle looks like it's significantly more reducing than that of Earth. It's somewhat paradoxical. Earth is kind of moderately oxidized, and then Venus, we have very limited data for Venus still, but the data that we have suggests the surface may be near this magnetite-hematite buffer, which is a bit more, significantly more oxidizing than this for Earth. And I would argue that the oxidation state of the surface suggests that the interior is more oxidizing as well, which would fit very nicely with an idea that Venus started off with water, lost a bunch, and then oxygen went into the interior. But I should emphasize, we don't know very much, so we of course need more missions to go to Venus in future. And so in a decade or so, once we've done Mars, many more Mars orbiters, sample return, and a few other things, we should really start thinking about going back to Venus again. But one thing that really emerges from thinking about this, caveats about the data aside, are what drives these bulk trends and what is the role of, in particular, orbital distance versus planetary mass, because you can see there's a trend in this direction, if this is correct, towards more highly reducing as you go outer in the solar system for these objects, but there's also a trend towards lower mass of the object. So that's one motivation. Another one is terrestrial exoplanet oxidation, so which is perhaps most relevant to this audience. And this is really rather simple. So Earth's oxygen atmosphere is produced by life. We've heard already this week that likely we're going to be able to observe O2 in exoplanet atmospheres at some point in the next decade when the ELTs come online. And this is really exciting. So perhaps this means that we can detect life on exoplanets. The picture, unfortunately, is more complicated because thanks to the work of troublemaking theorists, and I kind of count myself in this category partly, it's been shown that there are several ways in which you can get abiotic oxygen-dominated atmospheres, so without the presence of life at all. One of them that we looked at a few years ago was if you take a planet which is Earth-like in all respects, it just has less nitrogen in its atmosphere, you weaken your cold trap until eventually you reach a point where H2O can get into the high atmosphere. Then you can lose hydrogen, build up oxygen to a significant level that way. But then there's another mechanism which you've heard quite a bit about already, which was first put forward in this paper here, and it comes from the fact that M stars have high XUV and they have this extended pre-main sequence phase, so there's going to be a large runaway greenhouse period, and that has the potential to lose a lot of water and potentially create a lot of oxygen in the atmosphere as well. So based on this really interesting result, the question I want to focus on for the remainder of the time here is whether this is actually going to lead to abiotic oxygen atmospheres on these planets. And if you paid attention in Laura's talk, you will realize that the thing that you have to really think about here is that hydrogen gets lost to space if you have a steam atmosphere. You have photolysis of H2O and then hydrogen loss. But if you have a magma ocean present, which you will, if you have a significant amount of water in the atmosphere, there's going to be a lot of iron for that oxygen to react with. And there's potential as you're losing the oxygen as you're losing the hydrogen for the released oxygen just to go down into the mantle and remain there, as perhaps may have happened extensively on Venus. So our approach to this problem is to build a redox evolution model for planetary atmospheres. We couple stellar evolution, atmospheric escape, a bit of atmospheric chemistry, radiative transfer, and a magma ocean component. And we do this while tracking the redox state of each of our regions with using this, you can interpret in this kind of box model approach here. So here N is oxidizing power, and escape of hydrogen leads to an increase in oxidizing power, which is the reason I've drawn this arrow down in this direction. So it's complicated to take all these components and join them together. There's a lot of things going on, and one really big simplification we're kind of forced to make at this stage is to really limit the number of chemical species. And what we do is we say that hydrogen, iron, and oxygen are allowed to be redox active, but nothing else. We allow a role for CO2 in the radiative transfer part, but otherwise that's it. Another thing we do in terms of initial conditions, because we're looking for cases where you're most likely to build up oxygen, we assume the planet starts with a steam atmosphere, but without hydrogen. So we're not worrying about the initial hydrogen envelope stage if it's there. So now I want to go through these different components one by one and say in brief terms what we did. The first is the stellar evolution part. We focused on XUV-driven hydrodynamic escape, and 5 minutes left, yep. So we focused on XUV-driven hydrodynamic escape, and for this you need UV and XUV evolution versus time along with the bolometric curves. We use this sources for this information. I will just add that for the M dwarfs in particular, this is a case where more data is still really needed. We did the best that we could, but it's going to be absolutely fantastic when there's harder constraints for a wider range of cases on how XUV and UV evolve as a function of time. Atmospheric escape. So we are doing essentially an energy limited escape calculation, although we make some attempt to constrain the fudge factor. The way this efficiency factor that James Owen was talking about yesterday. And so the limiting cases we look at are one where it's constant and quite high, and then the smallest one is where we assume that the moment oxygen starts getting dragged along with the hydrogen, it's so good at cooling that it just shuts things down, and so the fastest you can go is hydrogen loss without oxygen. That's our lower limit on that. I will just add as well that we started off trying to use, and this is really for people who are interested in think about this particular area, we started off using the Hunter et al. Formalism, but it is, to me, a little counterintuitive, and the derivation was almost impossible to find. So we went back to the original equations, and I think came up with a way of thinking about it that is much more straightforward. So check out what we did there if that interests you. So there was an atmospheric chemistry component, and I should probably emphasize here what we weren't doing is like a really full atmospheric chemistry calculation all the way through the atmosphere in real time, coupling all the components together. Instead, we were focused on one very particular issue that we had reason to think was very important at the time. And this was this question that if you are in the high atmosphere and you have an atmosphere, so if you have H2O and you start losing hydrogen, you build up oxygen, is it possible that you self-limit the escape through a feedback which involves atomic hydrogen interacting with O2? And the reason we thought it was important is because this has been argued for many years in the solar system to be something that stops planets oxidizing, Mars in particular. And we used a 1D model to analyze this. And the result we found was that, in fact, there doesn't seem to be a clear shut-off mechanism at all. You get more of a quasi-linear dependence of the escape on the stellar UV flux on the atmospheric O2 concentration, which was kind of surprising in some ways, but actually correlates very neatly with recent developments in the Mars literature. There's been people that have worked on this and shown that on Mars as well, if you get H2O into the high atmosphere, you can circumvent this mechanism, and that leads to net overall oxidation. So then we did radiative transfer, which I think I'm just going to skip right over. It's a line-by-line calculation, but really fairly standard in most respects. We did magma ocean calculation, and I'm going to try and breeze through this as well because Laura did a really thorough overview of this yesterday. But the magma ocean depth varies as a function of the temperature. We allow H2O and CO2 to equilibriate. There's oxygen partitioning that goes reaction with these iron species. And then one caveat of what we did is that we did not include redox disproportionation. And so I think this is an important thing, and it would be interesting to include it in more detail in future studies. But that will likely require much better experimental data to constrain this process better. So let's skip now to model results. First, I'm going to talk about just the case where we don't... Is the mic gone? Oh, it's unfortunate. Batteries? Should I just use them for the sake of time? Shall I just use this for the last few minutes? Okay, yeah. So we did, first of all, calculations where we didn't allow interaction with the magma ocean, and that's what's shown in this plot here. I've shown it for some solar system planets and some exoplanets. We've got the TRAPPIST ones in there as well on another plot. Focus on the bold colors because these are the least extreme cases, the more realistic ones. And really the essence of what this plot is showing you here on a log scale is that the mantle FEO inventory is much, much larger. I think I'm running out of time a little bit. So this really shows the need to do a coupled calculation, which is what you see the results of here. That's the TRAPPIST data as well, if you're interested for that part. And what we find as a function of iron content of the mantle and H2O content of the planet, that there are regions still where you build up oxygen, but for a wide variety of planets that are wet with more mantle iron, you get almost no O2 building up in the atmosphere. And I won't explain in detail why that happens because I'm running out of time, but we confirmed our intuition on it by doing an analytic calculation and managed to roughly confirm that result with a simple formula. Well, also very important, we found that the model depended on orbital distance. So the further away you get from the host star, the much less likely it is that you're going to build up oxygen. And then we did sensitivity tests. This is a kind of summary of the key results. And I do really want to emphasize this point here because I think it's important. Laura talked about the initial study yesterday where we were looking at Gliese 1132b. I think as a planetary community, the most exciting thing for us in the next 5 or so years at least is going to be making observations of these planets which we know are too hot for life, because these are the ones which are going to constrain these models. These are the ones which are going to advance things so that we can understand how these processes work by comparison with observation. And once we've done that, we're going to be much readier for the challenge of making robust predictions for the habitable zone planets where life could be present. I just will do a very quick shout out to work by my very talented postdoc Feng Ding recently, who's been working on three-dimensional modeling of this exoplanet where we think oxygen could have built up. I will skip right over this part, which is interesting, but there's no time, and focus on the conclusion. So we've constructed a model to understand planetary oxidation. Results indicate that wet planets with iron-rich mantles do not build up abiotic O2 in their magma ocean phase. There's a strong dependence of the results on orbital distance. There may be dependence on planet mass, but there's multiple competing effects, and so we haven't really been able to tease that out yet. And I would argue the detection of O2, just given what we know now from this modeling in the atmospheres of planets like TRAPPIST-1Fg or LHS 1140b, would be a strong suggestion that life could be present on those worlds. So I'll leave future steps up and take any questions. Thank you.
I'm Dorian Abbott from the University of Chicago. If you found a planet with roughly Earth's mass and radius, and it was orbiting an M star, and you could tell that there was some nitrogen or CO2, and you found oxygen or ozone, would you think that that would be a good biosignature?
Some nitrogen, as in enough nitrogen to give you a nice cold trap.
Is that the biggest issue?
Yeah, I didn't get into the nitrogen at all here because, frankly, it's harder to. It's messier, and observing nitrogen is hard because it doesn't have spectral features. But if you had a way of diagnosing surface pressure and you could demonstrate that it was quite high, I think it would be an extremely interesting observation. I think I want to emphasize again, though, that what is going to make progress in the next few years is us building these models that work for sterile planets, the ones that we think are hotter and closer in, testing it, seeing if our ideas are making sense or if they're way out, and then ask me again in 5 years. And once we've done that phase of observation model into comparison, if things are looking good, then I think we can start making robust predictions.
All the way up in the back.
Martin Turbet from Geneva Observatory. I would like to know how much is the oxygen build-up in your model linked to the time does it take to go from the first crystallization of the magma ocean to the condensation of the atmosphere, of the steam atmosphere? Is it linked or not to how much O2 you can build in the atmosphere? Or? Yeah,
so that's quite a good question. It kind of all happens around the same time in a sense, because if you're really hot and you've got lots of steam, then, I mean, unless you're really, really blowing off vast amounts of hydrogen, there's always going to be enough iron to take up that oxygen and keep the oxygen from building up in the atmosphere. So it's the end phase of the planet, of the magma ocean crystallizing and the steam raining out, where everything happens in terms of oxygen buildup. And what the model is doing is really encapsulated in this equation here, which is kind of, the idea is that you, I don't think the time scale that we had in there is actually visible there, but you have the last period where the magma ocean is crystallizing, and you can kind of approximate an integral over that period, and that's the point where the majority of the oxygen is building up. And that's why it's so much harder in wet planets to build up oxygen, because you're getting to the runaway greenhouse limit, but they've still got thousands of bars of H2O in their atmosphere, and so you've still got tons of potential to get that oxygen deep into the mantle. Does that make sense?
Okay.
I'm afraid that's going to have to be our last question, but there is a 10-minute break right now. We'll come back at 6:10, and you can pounce him during that time. Let's thank him again.